Okay, so this is my last lecture, and so you won't have to suffer me anymore after this. So I just want to recap where we started. So my very first lecture was about what we know and what we don't know about QCD in the larger, bigger picture. And I tried to argue to you that there's a lot we don't know that's of really fundamental and intrinsic interest. QCD as a quantum field theory. Yeah. Right, so there's a lot we don't know. And so I also use that to motivate the case for a future electron-ion collider, which would be really this amazing multi-purpose machine that can collide electrons on protons, polarized or unpolarized, and electrons on nuclei at extremely high luminosities and high energies to really uncover some of those really mysterious aspects of QCD, which I argue to you are some of the most profound problems in theoretical physics, namely emergent phenomena such as chiral symmetry breaking, confinement, and other such non-perturbative things in QCD. And so the electron-ion collider really shows a lot of promise, and it will likely be built, hopefully in the next decade. And I'm saying this because I think, you are sort of the right age range where some of these ideas will become relevant for this machine, and so your work will certainly impact what we learn from such a machine. Then in my second talk, I focused on one of the aspects of interest for an electron-ion collider, and that's the physics of very dense gluon fields. And I argued to you that this physics is really like that of condensed matter physics or other many-body contexts in physics. And so the sets of questions that emerge are very different from what one thinks of in perturbative QCD. And it has its own set of well-defined formalism that one can employ to really get quantitative answers which could possibly be probed at or answered at an electron-ion collider. So that's one of the prongs of physics at an electron-ion collider. And so then in the next lecture, which is this morning, I talked about the application of these ideas about dense matter to heavy ion collisions. And I argued to you that in this Raju limit of the theory, which is one of the two well-defined asymptotic limits in which you can do perturbation theory, one of these being the Bjorkane limit, where the machinery of perturbative QCD really works very well, as you learned from Professor Spira's lectures. And then there's the other limit, the Raju limit, which is the one I argued was relevant for all these questions about dense gluonic matter, strong fields. And in the Raju limit, I argued that you can naturally perform quantitative calculations and really learn something about the nature of heavy ion collisions. And so that was sort of the topic of my first lecture. So I also then, this morning, and then if you recall, I went through some of the somewhat technical formalism of how one computes things. And the way I did it was using the language of Feynman diagrams, in some sense, in QCD, because I wanted to show you that within the language of Feynman diagrams itself, you encounter all of these complexities when you try to formulate things in conventional waves, in terms of, for example, the probability to produce 1,000 particles. But it's also the wrong question for heavy ion collisions. You're not interested in the probability to produce 1,000 particles. You want to understand what is the energy density that you produce in such a collision as a function of time, as a lifetime of the system. And you want to understand how these energy correlations evolve in time. Because we're interested in a transient property of that matter, not in its asymptotic state. And that's a frequent misunderstanding that people have about the aims and goals of why we do heavy ion collisions. The questions that we're addressing are qualitatively different. And so the formalism has to be different. But within this formalism, one can do quantitative calculations in principle order by order, weak coupling. Now, of course, there's a big question of what happens when the coupling becomes large and so on, which we are not really equipped to handle. At least we can work in the Raju limit in a systematic way. And I'm going to continue that discussion here in this lecture. So, and the question that we we addressed was, how do we go from this very non-equilibrium state, which is very violent at very early times, to thermal equilibrium in a system with very low viscosity to entropy density ratio, a so-called nearly perfect fluid. And so, but I should start out with a confession that in my last talk, I actually cheated you quite a bit. Okay? And the most egregious crime that I committed was that I matched the Glasma that I talked about in the last talk, where I did this factorizing of these fluctuations, and then I sort of computed the stress energy tensor to leading order, and I took the results of that, and then I matched that to hydrodynamics. And then I further bamboozled you by showing you the excellent agreement of that with data. Okay? And I said, oh, this is great. It all looks good. You can go home. But in doing that, I was leaving out something very essential. And that, well, kind of, like I say there on the slide, that changes everything. Okay? And so the motivation of this talk, the purpose of this talk is to tell you about what's missing, why it's important, and what some of the consequences are. So I just want to go back and remind you, so I had this very complicated looking slide, but trust me, it won't last for very long. And so if you want to look for more details, you can look at these old papers by Francois Gélis and myself. And so remember I said you could compute the inclusive multiplicity or the energy density, which are both similar quantities. This was in a scalar theory, but you can also do it in QCD, as I'll talk about, to leading order as a product of classical fields. And then I solved the classical equations of motion to compute the average inclusive multiplicity. But now if you say, when I go to NLO, so an NLO in this case is order G to the 0, but all orders in G rho, because rho is of order 1 over G. So you have to include all possible such sources in the computation. And then NLO, the expression can be written in this form, which has two terms. And one term can be thought of as a two-particle production in this background field of rhos, but where then I integrate over one of the particles to get the inclusive multiplicity. So that's represented by this. So the solid line is this cut propagator, which means that I really have these two particles which are here at plus and minus on shell. They're actually producing particles. And then the other term is actually a one-loop correction to one of the classical fields. So on one side, I have a classical field, and on the other side, I have a one-loop corrected classical field. That's denoted by this term here. And so you have two such contributions. One comes from, you can think of as quantum fluctuations in this background field, and you take the product of that. And the other corresponds to the classical field of leading order times the one-loop correction to the classical field. So, and in principle, one can go to NLO, NNLO, and so on. In QCD, you can write this in the following ways, that suppose I'm computing my energy density or some local operator, inclusive local operator, forward light cone, then I can think about this as a problem where at NLO, I have some quantum fluctuation which starts at minus infinity and then propagates all the way to the forward light cone in the background field of the classical fields. Okay, so I have the classical Yang-Mills fields, and then I start with some plane wave solution which evolves through these CGC classical fields, and then it sort of interacts with the classical fields that were produced after the collision, and then eventually kind of arrives at this point where I compute this energy density or similar inclusive object. So that's like a gluon pair production in the classical background field kind of contribution. And that was precisely this kind of term here. But then there's also a term where I could actually have a kind of loop in there, right? So it's a loop correction in the classical field. So I still have this classical field propagating here. And then I have just the classical field on the other side of this cut in momentum. And so this is a one-loop correction to the classical field. Okay? Now, what is truly remarkable and highly non-trivial is the fact that this kind of evolution can be rewritten in such a way that it can be expressed completely as a problem with retarded boundary conditions. Okay? So all I need to do is to specify the classical field at minus infinity and the quantum fluctuations to the vacuum at minus infinity, and then propagate the two together, okay, to compute this object at next to leading order. And so that can be formed in the following way. That's the structure where this is a propagator. So that's this, cut propagator that I talked about here, which is formulated on some initial surface, okay, which I had previously, which was this wedge here. And then there's this one loop correction to the background field, which also turns out you don't need to compute it here. All you need to do is compute it at this wedge. Okay? So again, similarly, this correction here only needs to be computed here. Okay? It doesn't need to be computed anywhere in this forward light cone. And likewise, this loop also doesn't need to be computed anywhere. It can just be computed in this wedge here. And this object, multiplied by some linear operator, which I'll talk about in a second, that acting on the leading order classical field solution is what gives me an NLO correction to the energy density or whatever inclusive correlator that I look at. And so what is this linear operator? So that linear operator is an object which is just a functional derivative which is actually just sitting on this initial surface here of the gauge field. And that's acting on the gauge field at this point x here. Okay? So this is a point x here. And so this object, or some place in the forward light cone, and this actually is an object which I can compute. Okay? Now, where I was cheating you was that it turns out that if I include modes, quantum modes, which are not traveling along the light cone, which are not static gluon fluctuations along the light cone, the moment I introduce some rapidity dependence in this quantum fluctuations. So remember, rapidity goes from plus infinity here all the way to minus infinity on the other light cone. And so the moment I step off the light cone, I'm sort of looking at these p plus not equal to 0 modes. And it turns out that for these modes, right, this linear operator is actually important. Okay, so I cannot just define for those modes things on this initial surface. Okay? For the p eta equal to 0 modes, right, in momenta, quantum modes, it's sufficient for me to just work on this initial surface, and that's where I get this Jim-Wilk factorization that I talked about. The moment I step across it, then I have fluctuations, right, which grow exponentially with time. So these quantum modes, they're not just dressing the wave function, they actually evolve into the final state. Okay? So there are quantum modes which are traveling along with the hadrons or nuclei, right, which are along the light cone, if you like. They're kind of closely along the light cone, and they're static in time, and they actually dress the wave function. Okay? But then the moment the collision happens, right, there are quantum fluctuations that are generated, and these quantum fluctuations cannot be absorbed into the wave functions. They just grow exponentially in time. Okay? And that's, in principle, a big problem. Okay? And in fact, so think of your leading order classical fields as being independent of rapidity. So they're the same anywhere. They are p eta equal to 0 modes. They're just all, sort of uniform in rapidity along the light cone in space-time rapidity. So now suppose I take this classical solution and I add a small quantum fluctuation, right, which is a function of eta. Okay? That means I'm introducing a momentum mode which is p eta not equal to 0. Okay? And what I find is that now if I solve equations with respect to this, so effectively I'm solving what I call small fluctuation equations, then I find out, and so this quantum fluctuation is parametrically much smaller than the classical field. So it's of order 1 over g, and remember, I'm working the limit where g is going to 0. Okay? So g going to 0 means that the classical field is very large, right? So if I have a classical, G, so this is large, right? And then little a mu, quantum, order 1, right? And this is order 1, right? So this is much smaller than this this object. So this is very small, okay, to start with. But as I mentioned, what you find is that these small fluctuations, they grow exponentially in time. So these are actual numerical simulations that were first done by Paul Ramachka and myself about, I don't know, 12, 13 years ago, where we saw that, if you solve the classical Yang-Mills equations in 3 dimensions with this very small quantum fluctuation, the modes of the pressure as a function of time in units of QS, they really grew exponentially as the square root of QS times tau. And the reason you have a square root instead of just an exponential is that we were working in an expanding geometry. Okay? So the system was flying apart at the speed of light, okay? And that changes an exponential to a square root. And this phenomenon is what's called in plasma physics, I mean electromagnetic plasmas, as a Weibull instability. Okay? And so this is a very generic thing in electromagnetic plasmas. Sometimes it's called a streaming instability. And then it leads to exponential growths, and that causes lots of problems in these electromagnetic plasmas. So these are actual physical things in electromagnetic plasmas that influence the construction of, tokamaks and so on. So this exponential instability, okay, plasma instability, what that does is just grows so fast that this fluctuation becomes of the same order of the classical field on a time scale which is 1 over QS times log squared of 1 over alpha S. Okay? So what I mean by that is that my small fluctuation A is of size, exponential of square root of QS times tau, right? And this becomes on the order of big A, right, which is of the size of 1 over G, right? So if I now invert this, I would find that this is 1 over QS. And then because of the square root, I have to take the log squared, right? So it's log squared of 1 over G. Right? So I take the log on both sides, right? That gives me square root. I square that. That gives me tau. So it's 1 over QS times log squared of 1 over G. So very, very fast. So the initial time scales in the classical field, the parametric time scale is 1 over QS, right? When the fields are large, right? So this is a order 1 over G at time scales 1 over QS. And then on a very, very short time scale, the fluctuations are the same size. Okay? Now you can say, oh, I work with resummations all the time, okay? I know how to sum when logs get large, right? I know how to resum logs in X, right? Maybe I can do the same resummation. Now, when you do such a resummation, you can try and do that. And then what you do is you sum all contributions which give you such exponential enhancements, and that can be enhanced. And in principle, it turns out you can write this resummed energy momentum tensor. So this is the energy density and the components of the other pressure components of the stress energy tensor. You can rewrite that as an integral over the spectrum of initial fluctuations. So I can start with many different initial fluctuations, and there's a distribution of these initial fluctuations. Okay? And this times the classical field, but now the classical field is evaluated at this classical field A classical plus this little a. Okay? And so I have to average over this little a, and then I have to do the average over the rows at the end. Okay? So that's the kind of idea. So the way you can see it actually more microscopically is as follows. So now imagine I have this classical field which is evolving in this forward light cone, and then I'm doing small quantum fluctuations around it. Okay? And so the propagator for that can be written in terms of these small fluctuation products of these small fluctuation fields, where the minuses and plus indicate that this is G plus minus. I didn't write down. And so this is again obtained by solving the small fluctuation equations of motion for the small field. Okay, and you can compute the eigenvalues and eigenfunctions for that. And then you can actually, in principle, compute this. Okay. And so in terms of that, right, this resummation corresponds to actually replacing this F int by this form where here is a small fluctuation propagator of these classical fields, which is then defined on this initial surface. But this initial surface is now this surface, this Cauchy surface in the forward light cone. So I don't have to worry about the Cauchy computing this everywhere. I still can use retarded initial boundary conditions, but these are retarded conditions now on this surface here, not on the backward wedge. Okay? So I need to really know what the non-trivial classical fields are in this wedge and solve these small fluctuations equations, the background of this classical field, and then compute this propagator, and then use that to compute the energy density, the forward light cone. And so you can do this. So this is the way you get this is by you're resumming terms like this, because this has the same magnitude as this term here, right? So I have this exponential growth to the order 4. This diagram is the same order as this diagram, and that means you're ignoring terms which are of this sort here. Now, this is a bit of a problem because this term is suppressed compared to this term only up to a time scale which is an additional log in 1 over g. Okay? So when you start doing this process, it gets very, very, very dangerous, okay? Because these contributions are becoming very, very large, okay? And so in some sense, the resummation program that you do in the forward light cone is extremely fragile, okay? And it actually shows you that there's a certain limitation at some level to how far you can go from first principles in quantum field theory and computing things in the forward light cone. And in some sense, you can say, this is a failure of your entire program, okay? But some magic occurs, okay? And I'll come to that magic in a little bit, okay? But I just want to point out that if you really are, a hardcore guy and you say, okay, let me do resummations and so on, you'll find that you can resum these kinds of contributions, but then these contributions are smaller, but they're only smaller up to a time scale which is then the next log in g, okay? And this is the difference between logs and exponentials, okay? So if you have, things that are growing exponentially, right, they're very hard to resum in a consistent way, all the time. But if you have logs, you can handle those, okay? So the logs in x that I had, in BFKL and or the logs in Q squared that we had in DGLAP, those are manageable because logs, don't give you this very, very rapid growth. So the validity of your approximations are valid for a very long period of time, a very long range in those variables. But in time, and these are so-called secular divergences that happen in condensed matter physics all the time. You get very large growths in time. And in fact, the Boltzmann equation can be thought of as a resummation of a certain sort which sums certain classes of secular divergences consistently in certain approximation. So suppose you try to derive the Boltzmann equation from quantum field theory from first principles, doing diagrams, okay, then you encounter these kinds of secular divergences, and the particular resummation of those secular divergences is the Boltzmann equation. That's one way to think about it. But anyway, let me still write what I have. So if I include all leading logs in x and leading log instabilities, okay, I get the following. I get these factorized w's, right? This is still true. So these are these weight functionals which carry all this information about these many body gluons in the wave function. So that's here. So that factorizes. But then I have now this object here, which comes in from the spectrum of fluctuations in the forward light cone, multiplied by this T mu unit leading order, which is then shifted by this little a. Okay? So this is about as far as one can go. Okay? But it's still not bad, right? You could say, well, okay, you have some predictive power in some region, and this is fine. Okay? But then the problem is that, as I argued, that once you go to next order, this becomes problematic. Now, before I get to talking about what happens in QCD, these small quantum fluctuations, they do something also pretty remarkable, okay? So imagine now, so think of it in a physical way. So you have these two condensates, right? These two color glass condensates, which are very high occupancy classical fields. And they collide, and they produce another high occupancy classical field. Then the problem is in heavy ion collisions is that how does this system thermalize? Okay? But before they thermalize, you can ask another question. You can say, how does this object actually decohere? Okay, it's a highly coherent state. Okay, how does this object even, how can I even decompose this object into particles? Okay? I mean, remember, I'm working in weak coupling, right? My coupling is going to 0. Okay? And so in weak coupling, I would think that if I have thermalization, I should have some notion of particles, of quasi-particles. Okay? But all I had initially was a classical field. How does this classical field become particles? How does decoherence take place, you know, in sort of to first approximation? Okay. And so it turns out that one cannot prove this absolutely from first principles because QCD is very complicated. But we strongly suspect that these Weibel instabilities that occurred very early times, they scramble information, okay, that is contained in these classical fields. So the classical field contains information about n-body correlations. And what the Weibel instabilities do is that they kind of scramble that information, okay? Because the problem of thermalization is a problem of energy, of memory loss. Okay? You're losing memory of your initial conditions, okay, when you thermalize. And so the question is, how does memory loss occur? Okay? And so the first step in that is you have to decohere information, okay? And then that information can thermalize. Okay? And this is exactly analogous to what people in the language of black holes, okay, used to understand, thermalization or how black holes thermalize. Okay, and in fact, there's a paper by Maldacena, Stanford, and Schenker, where they actually argue that black holes actually give you a bound on how quickly such black holes can thermalize. And this bound actually is very close to what one gets here. Okay, so if I had a Yang-Mills theory in a static box, not this expanding situation, my small fluctuations would grow exponentially. Okay? And in that case, right, one can show, right, at least parametrically, that it's at the same order as the Maldacena, Stanford, Schenker bound. And so that's actually very interesting, sort of from a fundamental point of view. And then it's an interesting question to discuss coefficients. And this is something that Zoran doesn't know about it yet, but this is a common research project we're going to have. But anyway, but in the expanding case, it's actually not as, because it grows as exponential of square root, the scrambling is slower in that case, somewhat slower. You have log squared as opposed to log. And so then you get you don't satisfy this Maldacena, Stanford, Schenker bound. But so this is a process of scrambling. So what I'm going to talk about is in a classical theory how you see such scrambling. Okay, and so the basic idea is that when you do a path integral over multiple initializations of classical trajectories in one event, and that comes because you have these quantum fluctuations. Okay? So in each event, I can have quantum fluctuations, but then I can have a spectrum of those possible quantum fluctuations, okay, with some distribution. Okay? And that distribution is actually what leads to what is called, in the literature, it's called eigenstate thermalization. And this was actually discussed, I think most at least to me, most understandably by Srednicki, but also by Michael Berry, and then there's a lot of papers by Riegel and collaborators and so on. Okay? So let's try and understand this. Huh? Yeah.
So you have here, anyway, the classical field itself has different initial conditions and you are integrating over that, right?
No, so these are two different things, right? So what I'm saying is that, so when you say different initial conditions, you mean different rows, right?
Yes.
But so you have to think about each row, right, as a given event, okay? And so my question is that once I have this given event, can this event thermalize, okay? And so for this given event, I can have a possible spectrum of fluctuation. So indeed, I have a double quantum average that I'm doing in which I'm separating the two out. Okay? But again, the logic is that one is on very different time scales than the other. Okay, so in some sense I have a double quantum average. Again, it's like this replica idea coming back, right? You have an integration over all possible events, but then you have integration over all possible fluctuations in any given event. Okay? And I'm saying that this scrambling occurs already at the level of all possible realizations of fluctuations in a given event. Right? So what I'm saying is that if I have a given classical field for fixed rows, right, that classical field can have a multiplicity of possible quantum fluctuations that one can have.
Yeah. But isn't it true that in a given event itself, your source has somewhat stochastic because it's has some amount of some amount of stochasticity in it, right?
No, because I fixed rho, right? So I've of course picked rho from a stochastic distribution, but then I fixed it, right? And so I cannot no longer vary it. And then, but then in that event, how does thermalization occur, right? And so then there has to be another source of that, okay? And so that source is coming in from, in our case, it's coming from Weibull instabilities, which are just growing very rapidly, or in the case of scalar theories, it's coming from parametric resonance, quantum fluctuations. Okay? But those fluctuations are picked from a different source from these rows, right? I mean, I'm computing a spectrum of fluctuations. So let's take the early universe, okay? That's a good example. The early universe is one event. That's my rho, okay?
Yes, but even in one universe, we have fluctuations.
Exactly. That's my point. That's like the exact analog, right? So my one rho collision is one universe. It's my little Big Bang universe, okay? And in that little Big Bang universe, I have fluctuations. And by the way, this thing that I wrote here of this F, this is what people in high energy physics and cosmology call the spectrum of Gaussianities or non-Gaussianities. Okay?
No, what I'm saying is something similar to what CERN was doing. For example, you could say that there's a fluctuation, the two-point function fluctuation in A classical, but that also has some kind of source coming from the from the hard part, I mean, from the x greater than xc part.
Yeah, but that's what I just did here, right? This is exactly what I was doing. I mean, if you remember, I had this expression.
No. So in this case, what you're having, you have a source for the one-point function, but not for the two-point function, right?
No. This is, why do you say that? This is just this will be for, you know, in principle, all endpoint functions. This was true for a generic operator. This is not just for T mu nu, right? I just chose T mu nu as an example, but this is true for any inclusive operator. Okay, so in my previous slides, I had O, in fact, okay? I didn't call it n charge, but it's true for any inclusive operator.
So what I'm saying, if you want to compute for a specific event, your J is something that that is drawn from the stochastic distribution and is fixed.
Right, that's my universe.
Yeah, but in a specific event also, you can have something that sources a two-point fluctuation on top of the...
But even there, so there's two issues, right? They can be two-particle correlations which are related to static.
Yeah, which comes from initial conditions.
Yeah, so those, exactly. So those are there, right? But in addition, I can have endpoint correlation. I mean, so what I'm saying is that any endpoint correlation that I compute will have two sets of contributions, right? One is an averaging over the set of universes that I have, and the other is an averaging in my particular universe, right?
Right.
So what I'm talking about here is about the averaging in my universe.
Yeah, but I think in this particular way of doing things... At the
end of the day, I have to average over all possible universes.
So in this particular way of doing things, you're not taking into account the initial fluctuations that are already there in the two-point function or something.
No, I am, because, I mean, at the end of the day, when I finally compute my result, right? So let me show you my final result that I wrote. When I write this final result here, right, I have a double average, right? So that double average also includes the averaging over all my possible universes with their different weights. My different universes come with different weights. But then I also have this averaging in my single universe. So any physical observables, because this averaging cares about color, must include both averaging simultaneously. I'm just saying that there's a certain time scales involved for each given row, I can still have thermalization. Okay, but at the end of the day, I have to do an event average as well. Okay, so I can find thermalization in some single large event, but then I have to average over all possible events. Okay, yeah.
So in order to match theory with experiment, you have to not only know what is average of t mu, but you have to also match the statistical fluctuations of t mu.
Exactly. So that's why heavy ion collisions are more difficult than the universe. Okay? Because in the universe you have one event. But on the other hand, it's also gives you also more observables you can compute, right? Because in a heavy ion collision, I have billions of events, so my data, I have a lot of data, right? So I can sort of, even for lower moments, I can learn something. So in the early universe, to learn something, you have to go to Legendre polynomial numbers of thousands and so on to see some real structure. While here, I can see it in a few moments, right? Because I have lots and lots of statistics that I can vary in the two cases. So thank you. That was a very useful clarification.
And it's also consistent because if we have a completely unitary theory, there is no meaning of thermalization. So once you just sum over, you do this
Exactly.
splitting of sum in this way, I guess.
Right. So what Sayantan is saying is, like I mentioned earlier in my talk, what you see in the detector is not an energy density. You're just measuring, well, you can interpret something as an energy density in your detector. That's a physical observable. But it's coming from all these thousands of particles that are being produced, right? So if you're just looking at these thousands of particles, well, what do I care? What is this energy density? So the energy density is an interpretation of that thousands of particles, which is hidden in what's happening inside this integral. Okay? So you don't measure thermalization in your detector, right? You just see some particles. But you want to infer from that whether that stuff that came out was at some point in time, was it thermalized before it then fell apart and then went out of equilibrium again, right? That information is contained in the time evolution of this object here. This object here knows nothing about time evolution. It's completely static, okay? So it knows nothing about anything thermal, right? It's just separate universes, if you like. All the information about time evolution is contained in here. So if I want to discuss the question of thermalization, I can, for the moment, ignore these rows, okay? And that's kind of, I think, the most pointed answer to your very good question. So, and that's why I said here also in one event, okay? And so this is called eigenstate thermalization. So let me kind of work that out in a very simple example, okay? And this is a work that I did with Kevin Dussling and Applebaum and Francois Gélis in 2011. And at that time when we did it, we didn't realize that there was similar work that was done by Berges, Veterick, and someone else in 2004. And they called it pre-thermalization at that time. So, but this was done in complete ignorance, I have to say, of what they did. And also we formulated it differently. Anyway, consider the toy example, not QCD, of a scalar phi-4 theory. Okay? And now imagine that you have some time-dependent field which can be obtained by some classical field plus small fluctuations about that classical field. And this small fluctuations includes information about this little a that I wrote here, and that's given by this chi, and that's obtained by solving these small fluctuation equations of motion that I have here, okay? Where I can extract the eigenfunctions and eigenvalues from this equation. So it's a linear equation. But now I put in some information that these fluctuations, right, this object here, so Ayan, I'm assuming that these fluctuations are Gaussian now, okay, so in this thing. So these fluctuations I assume are Gaussian random, so they are seeded by just Gaussian random numbers, right? So this small fluctuation field is my little a, so this, and it's Gaussian, so it's seeded, if I expand out my a, so I have my little a, right? And if little a is a Gaussian field, then I can write this in terms of some ck times something, right? And this is then a Gaussian random number, okay? So that's an equivalent statement in momentum space. that this is Gaussian. So this is a statement, an equivalent representation of a statement by Berry. It's called the Berry conjecture, okay? That he said that suppose you have any classically chaotic system, okay? Any classically chaotic system, and if you look at its eigenvalues, right, you can sort of think about the, write down the eigenvalues of such a system. And now if you look at and you quantize the system, and you look at its high-lying eigenmodes, okay? Not the lower ones, but the higher ones, the more energetic modes. If you can show that these can be rewritten in terms of Gaussian random variables, if the density matrix that describes these modes, right, is a Gaussian density matrix, then the system will exhibit something called eigenstate thermalization. It will look thermal. Okay, the system, even though it may actually not be thermal in a canonical or grand canonical sense, it will microcanonically look like a thermal system. Okay? And so that was kind of the statement by Berry and then developed by Srednicki and others. Okay? So here's the concrete representation of what I mean. Like suppose now, yeah.
That H is the Hamiltonian. What is H?
What is? So H. Oh, sorry. These are. I apologize. So these are Hankel functions. Okay. So I'm very sorry. I should have said this. So when I didn't write out something, which is usually you do an expansion in Fourier series, right? I'm taking some field in X, right? And then I expand this out in a Fourier series with some coefficients, right, times the phase, right? Now, it turns out when you do things in kind of curvilinear coordinates, in tau and eta, okay, it turns out that it's actually a better way to represent this in terms of Hankel functions. Okay? They satisfy the same orthonormality kind of properties that you need, okay? And so these Hankel functions are actually part of the solution of what this is. So thank you for that question. Yeah, so it looks mysterious, that, but this is a Hankel function with imaginary argument. Okay? So it's a well-known, so you can, a Hankel function is a linear combination of a Bessel function and a Neumann function. Two special functions. And they have very interesting orthonormality properties, and you can construct a complete basis and so on using these functions. Okay. So if you have now the scalar theory, right, and then you just solve the equations of motion for the classical field and the small fluctuation field as a function of time. Okay? And then I can compute T mu nu, okay, and I can compute this at next to leading order even, right, using my tricks that I mentioned. And then if you look at the energy density and the pressure, so this, and let's say I do it in 1 plus 1d even, so okay, so I have one spatial dimension and one time dimension, and then I evolve this field, right, phi. It's quantum mechanics, right? So it has just spatial dimension in one dimension, and I evolve it in time. And then I look at T naught naught, which is the energy density, and T11 is the pressure, okay? So if this is, so remember that for a free conformal field, E equal to 3p, right? So in a conformal theory, right, my energy density is 3 times the pressure, right? If I look at this, right, I find that they're totally disconnected, right? So the pressure is fluctuating like this, and the energy density is like this flat line, okay, in this theory. But now I introduce these small fluctuations, and I compute this, to NLO and average over all these fluctuations. And then I see very quickly, right, that this energy density goes to, so 3 times, so E is equal to 3p, okay, at this point here. So you have a single valued relation between the energy density and the pressure, which is very important for hydrodynamics, okay? So I can actually do hydrodynamics in this theory, just from this kind of stuff without talking about thermalization at all. And so what this is showing you is that this very coherent classical field, which is of high occupancy, so phi is of order 1 over g, right? When you have quantum fluctuations, those quantum fluctuations, they can actually grow, okay? They grow by parametric resonance. So there's a fluctuation, then you get these Lyapunov exponents, which give you exponential growth. You can resum those as some spectrum of initial fluctuations, just like I did for the Weibel instability. And this spectrum of initial fluctuations, that's what this object here is, okay? This contains information about the Lyapunov coefficients, which are these instabilities in the solution of this equation here. Okay? So let me recapitulate, okay, in case I wasn't clear enough. So what you're doing is you have classical fields which are large, right? The phi is of order 1 over g. Now I introduce some quantum fluctuation. So the solution, the quantum fluctuation equation is given by this. Okay? Now it turns out that this lambda has modes which such that lambda squared is negative. Okay? And when you solve the equations, it gives you exponential growth of this chi here, okay, naively. And so what you can do is you can resum that exponential growth. That's parametric resonance that you're seeing there. And then you can rewrite this into a spectrum of fluctuations or the evolution of just a classical field. Okay? So then the new classical field is this original classical field plus this object that you got from the spectrum of fluctuations, and then you can solve that with time. So what I was describing earlier was just this solution here, which is this object here, right? But now when I include this averaging over the spectrum of fluctuations, okay, this averaging over the spectrum here, I find that I get this single value distribution. And this is the essence of what people call pre-thermalization in the literature. And so my claim, which I cannot prove analytically from first principles so easily, is that one has the same thing in the Quark-Gluon plasma, in the Glasma that I was talking about.
What decides the time scale which will equilibrate this?
So there's some characteristic time scale which is related to your spectrum of fluctuations, right? And so whatever is the variance of your initial spectrum of fluctuations is what will set that time scale. So if your gauge, so in the case of QCD, it would be QS. Parametrically, that will set that time scale. Okay. This is not thermalization. Yeah. This is pre-thermalization because all it's saying is you have decoherence, right? All I'm saying is you get E equal to 3p. It doesn't mean that it's thermal. In fact, I will show you in a minute that it's how it works, okay? And so, well, actually, so that's the thing, right? I'm always looking at modes which are, well, first of all, I'm just doing this in 0 plus 1 dimensions, right? So I'm not, I'm only including, so again, I'm only including a certain class of small fluctuations, right? Those that grow exponentially, and that happens in the infrared. So if I computed, what I mean is that if I computed T mu nu at NLO, right? So if I included the loop, right? Then that T mu nu, the full T mu nu would include terms that are UV divergent. Okay? For the purpose of what I'm doing here, I'm not including those UV divergent terms. I'm only including those terms that have grown, that grow large parametrically with in parametric resonance with the classical field, and those are IR modes. I'm not including the full T mu nu at NLO. Okay. Well, so I work in a box where I'm not sensitive to really, fully UV modes. I'm always looking at modes that are not very sensitive to that. I mean, so what I'm saying is that at NLO, right, I'm explicitly cutting out terms which are sensitive to the UV cutoff. Because my purposes are different, right? I'm not trying to solve the energy density of the full phi to the 4th theory. My point is to illustrate, right, where eigenstate thermalization comes from And you can show, right, that you get a kind of scrambling which comes from the, so the very rapid growth of things in the infrared. Yeah. That's what. Exactly. This is exponentially fast. So Lyapunov exponents. This is coming from. Oh yeah, absolutely. I mean, this is not very robust for arbitrarily late times, or this is just to illustrate the role of Lyapunov modes in scrambling information, and that happens actually in the infrared. Right? So the growth of Lyapunov modes is controlled by infrared modes. Yeah. Right. Yeah. Yeah, I mean, that's the thing, right? So like what Zoran just alluded to, the time scales for that are not exponential time. I mean, they are much longer time scales than the time scales I'm talking about. Right? Because these things are growing really exponentially, right? So what I'm saying is that the small fluctuation is becoming of the order of the classical field on a time scale which is very small. Okay, so it's just an illustrative example. It's not meant to look at this energy density in the scalar theory, NLO to all. So I'm only including those contributions that really play a big role at early times. So this is early time physics, if you like. Okay, in the scalar theory. So now, exactly the same, oh, sorry.
Yeah, my question is related to that thermalization time scale or something like that. So maybe I missed something, but when we are not in a non-thermalized medium that is yet to be thermalized, how are we gonna define this P, epsilon and all these, epsilon equal to 3P? Because all I know that they are thermodynamical properties. In a thermalized medium, I can define all these characters like pressure, epsilon, which are dependent on my temperature and chemical potential. So
thank you very much for asking that question, because actually it's not true. Okay, because so indeed, the original discussions historically of things like pressure and energy density and so on have been came from thermodynamics, right? But the pressure is something that it's a well-defined object. It's just it's a component of the stress energy tensor. Okay, so suppose I write down QCD or scalar theory. I can write down the Lagrangian, and I can explicitly compute the stress energy tensor. And the pressure is just one component of that, right? And the energy density is another component of that. So there's no concept of thermal at all, right? So what is when things become thermal is that when you can define both of these quantities, okay, as extensive quantities which are functions of some common variable like a temperature, right? So what I mean is that, so I can always define, all the components of T mu nu. So once I start from the Lagrangian, I can just write down T mu nu, okay? And so I can define energy density and pressure, okay? No problem, right? But to make this statement that this is some function of temperature, and these are related to each other through some common temperature, right? So that this goes as, something, so basically that the energy density the pressure is the speed of sound, right, times the energy density, and these are all functions of a common temperature. That's a statement about thermodynamics, okay? So this statement is much more general. What I'm saying is that already from this exercise, so now I just solved the equations of motion from the Lagrangian along the lines that I suggested. I already find this without even defining concept of a temperature, okay? So it mimics something that looks like a temperature in a conformal theory. Okay? But I'm saying it's not genuine thermalization, okay? Because there's a sense in which this temperature is very important to define what is meaningful about thermalization in the sense of a canonical or grand canonical ensemble, okay? That we understand from StatMech thermodynamics. So anyway, thank you for that question. That's an important clarification. So let me now come back to QCD, right? So remember I said, you know, how did I start out, right? I started out with my classical Yang-Mills equations, and then I did small fluctuations around that, and then I found this exponential growth as square root of tau. And then I found that if I now try to compute it order by order, it's a mess, right? I could do some resummation, but then the next order is kind of gets to be large very quickly on log timescales, okay? And then I said some magic happens, right? And I'm going to tell you about magic, okay? Here. So sometimes magic works in physics, but actually it often works in physics. But and so let me just kind of tell you about magic here. So now here's my classical solution, okay? So what I plotted here is a distribution. Let me call it a single particle distribution, okay? It's just the product of gauge fields, the Fourier transform of that. So this is a function of proper time, tau. It's a function of the transverse momentum, and it's a function of nu, which is the Fourier transform of the of eta, okay? It's a Fourier transform of this object eta here. So it's what I called P eta earlier, okay? Or close to it, with a factor of tau here and there, okay? And so on this axis, I have the transverse momentum, and on this axis, I have the eta, okay? So remember I said that the classical field is boost invariant, right? It's independent of eta. So the classical field has P eta of 0, right? Because the Fourier transform it's independent of eta. And that's why this thing is only, it has zero support in eta here, so it's really at eta equal to 0. So this is my Glasma classical field, okay? And this is a classical field that's formed in a time scale which is 1 over qs. That's when the field is of order 1 over g. But now what I do is I tickle this field, okay? I just do a little small fluctuation around that field. And then you see these are actual numerical simulations that were done by Bjorn Bjorn Schenke and Zoran Schlichting. I was going to say Bjorn Schlichting and Zoran Schenke. But anyway, so this is a paper that we have actually only in a conference proceeding, actually, but that's still there. And so what you find is that, you know, you find that there's this instability in this eta direction, okay, in this rapidity variable. This isn't momentum. This is momentum quantity. Here it's this rapidity wave number. And then you see that on a time scale, which is very small, okay? Very small compared to this time scale. It's only log squared greater than that initial time scale. It has already become overoccupied, okay? There's a distribution in eta which is large. So this is an incredibly rapid process. So what this is telling you is that my classical field solution really changes dramatically on very short time scales to this thing here. So this, by the way, is a result of very, very, you know, sophisticated simulations, and I'll very briefly mention it, but I think Jordan will talk about this at greater length in his talks. Actually, I'm not even sure I do say it. I can't remember if I put it in my slides, but this comes from solving Yang-Mills equations in 3+1 dimensions on extremely large lattices, okay? And so you need that to resolve this dynamics that's going on in here. So here's the picture, right? Two color glasses, two sheets collide. And the classical solution of that plus quantum fluctuations leads to plasma instabilities on such soft timescales. And then this very anisotropic distribution becomes very quickly isotropic in transverse momentum, in longitudinal momentum. Sorry, this is transverse momentum, excuse me. Well, f of p, right? It's all of them. And then the question then is what happens afterwards, okay? So my claim is that this is pre-thermalization. So what is seen here is kind of pre-thermalization, because on this time scale, I can decompose my classical field in terms of single particle distributions and have it be meaningful. Okay, I can define quasi-particles, okay, which carry some transverse momentum and wave number in this time scale. And so what's actually going on, right? What do I need for thermalization to occur? So there's a natural competition when I'm trying to thermalize a system. So thermalization, so this is a plot in momentum space. So one definition of thermalization is when the distributions of particles are isotropic in PT and PZ, right? Because then I can define a temperature for this isotropic system, right? And which is the same in both directions that you have. So I have some kind of thermal system in 3 dimensions. So locally you can define that. Now, so it turns out there's a competition. On the one hand, the Quark-Gluon Plasma, the Glasma is expanding into the vacuum, right? So because it's expanding, there's a kind of redshift where all the particles that are remaining in some rapidity that I'm looking at is getting squeezed in the PZ direction, okay? While the PT is, it's happening very fast, okay? So PT doesn't have a time to change, and so it's getting redshifted here, and that's happening in momentum space like this. Okay? So you're going away from thermalization, right? Because if you have this expansion very rapidly, then in PZ, things are getting squeezed, right? While in PT, they're still large. So it's very anisotropic. So it's not thermal at all, right? But now what you need is you need to have interactions that are going to push things out in PZ, okay? So the interaction will scatter and you'll push things out in PZ, and the hope is eventually that'll thermalize, okay? So if the interactions become strong enough, fast enough, then it will beat the expansion, which is trying to make things anisotropic, right? So I mean, what could happen is, suppose the interactions were not strong enough, the system could just become very, very anisotropic and just free stream, okay? There could be no thermalization at all, okay? However, the interactions are starting to become strong and they can compete with the acceleration of the system, which is getting slower and slower with time. So initially the acceleration is huge, okay? But then as a function of time, the acceleration slows down and springs can catch up. Then you have a chance to thermalize the system. And so anyway, so yeah, so I did include some slides here. So, so here again, so this is sort of the formal way to write what I did here. So I can take my classical field, which is now a function of tau at some initial time, x perp and this eta, okay, and I can rewrite it in the following way with some weight, which is square root of the single particle distribution, times your, times this, random variables, so sorry, this is, excuse me, this is my polarization vectors, which is these Hankel functions here, times my random variable. So I just introduce some random variables here, right? And then I can compute my classical field. Okay? Now this is, in full disclosure, right? This is really coming from kind of an idealization of this more first principles problem that I had where I was trying to compute the spectrum of fluctuations on the initial light cone surface, right? I kind of gave up on that. But I still took the essence of it, by which I said that, oh, I can really roughly represent that by this object here. Okay? I assume that the fluctuations are Gaussian, right? I'm not including non-Gaussianities in my initial spectrum of fluctuations, and I'm parameterizing it to be of this kind of general form, and then I can kind of play with this form here, okay? So I can choose this function to have different kind of possibilities. I can assume the initial function to be like this, like that, okay, in momentum space. It can be prolate, oblate, whatever, right? I consider all possibilities which could mimic all the possible non-Gaussianities that I can have in this initial state. So I can control the prolateness or oblateness with this parameter psi of the initial momentum distribution that I'm now going to simulate. So the actual calculation is you're solving Hamilton's equations in 3+1D, SU2, gauge theory in a fixed gauge, which is called Fock-Schwinger gauge. You have to fix the residual gauge freedom and so on. I think Zorn will perhaps talk more about these things if he has time. And then these are extremely large numerical simulations. So the lattices are 256 squared times 4096. Okay? So you really need these large lattices to capture the very soft infrared modes in the theory. So again, this is classical statistical computations and weak coupling, blah, blah, blah. And we work at very weak couplings to make sure that the classical statistical approximation is valid. Okay, so here's the result from the simulation. So this is the longitudinal pressure divided by the transverse pressure. Okay, so like regarding this question that you asked there, right, this is, I can compute pressure without any notion of thermalization, okay? And I'm computing the ratio of the longitudinal pressure divided by the transverse pressure. And I'm computing this for very different initial conditions, prolate, oblate, all possible initial conditions. And so I noticed several things, and I also vary the occupancy of the fields at the initial time. Okay, I can do that also. So I change my initial conditions. And you find that, first of all, two things. The longitudinal pressure divided by the transverse pressure becomes smaller and smaller. I'm going away from thermalization. I'm not going towards thermalization. I'm going away, okay? But all of these curves are kind of starting to look the same, even though they start from very different places. This initial condition starts like this and goes here. This starts from high up there and goes there. By this time here, they're all starting to look the same. The same thing if I vary the initial occupancy, they're all starting to look kind of the same. And you think, well, is this accidental or is there something more to it? Okay? And what you can actually show, okay, and I'll show some slides to that, you can show that actually what happens is incredibly interesting and profound. Okay? What happens is that you start this Glasma, okay, at some initial time. And you can start the Glasma with very different kinds of initial conditions coming from all kinds of quantum seeds. And the statement is that regardless of that, the system does not go directly to thermal equilibrium like this. Okay? It actually goes to something else. And that's what we could call a non-thermal fixed point. Okay? What that means is that the properties of matter at this point here, just like for thermal equilibrium, right, are independent of the initial conditions. They don't retain memory, so that information has already been scrambled for you, okay, very quickly. And so it's independent of the initial conditions. You can start from any different initial condition, it goes to this point here. Okay? And the other really remarkable thing is that this non-thermal fixed point, as you change time, it evolves in a self-similar way. Okay? So it has the same kind of, you can map the properties of that system at one time exactly into the properties at some other time through some just variation, scale variation of some pure numbers. Okay? And so that's really remarkable. Okay? And then the point is that eventually this non-thermal fixed point goes into thermal equilibrium. So this is highly non-trivial because people always thought, okay, you have some initial conditions and you go to thermal equilibrium, but the claim is that there's an intermediate step there and you create a kind of matter which is non-equilibrium matter, which is interesting in its own right. So someone asked me this question, this guy looking at his computer right now. So you asked me this question that, about the Glasma, you were saying, okay, why do you call it the Glasma and so on? Well, this tells you that, the properties of matter here may actually be universal, okay, in the sense that they don't care about the initial conditions, and they may have non-trivial structure of their own to be of interest. Okay? And there are other examples that I will talk about if I have time of non-thermal fixed points in other systems, which are kind of just like the Glasma. Okay? So this really addresses the question you raised earlier. So now we can go back to looking at a computer. Okay? So now, so what is this universal non-thermal fixed point? So again, more specifically, if I have a single particle distribution, which is a function of p per pz and time, you can take this distribution and rewrite it. So he really did go back to looking at his computer. It's okay. It's okay. I was just making a joke. Okay, so anyway, so please feel free to look at your computer. Okay, so but anyway, so you can rewrite this as some overall power of time times some stationary function. Okay, this function is the same function at different times. It's just that you have to rescale the transverse momentum and the longitudinal momentum by some power of the time, which are given here by beta and gamma. Okay, and then there's an overall cooling time of this distribution, which is given by this term alpha. So what I mean is that suppose you have a function which is a Gaussian, right, at one time. At the next time, it's also a Gaussian, okay, but it might not seem like a Gaussian to you, right? But then if you rescale the variables of pt and pz there by time, right, you'll find that it can be mapped onto the Gaussian that you had at the earlier time. Okay? So it's still the same function at all times. So it's a stationary function. So it's just like in thermal equilibrium. In thermal equilibrium, you have a Bose distribution, right? Or you have a Fermi distribution. That distribution is always the same at any given time, right? And so this is something that is a kind of quasi-stationary distribution, which is also kind of universal. It's the same just function at all different times, independent of the initial conditions. Okay? And these plots actually demonstrate that from these numerical simulations. And so what you can show is that if you compute the moments of this distribution, that's the 0, 1, and 2 second moment. So sorry, this is a 0 and second moment. Then you find that these are at very different times, and all these curves all just lie on top of each other. Okay? And by looking at these curves, you can extract what the values of alpha, beta, and gamma are. And the statement are that these are universal quantities which carry fundamental information about the structure of the non-equilibrium structure of your plasma, your Glasma. And so this is in longitudinal momentum. You can do the same thing in transverse momentum. You see that all these different curves, they look the same at different times. So I can just map these curves onto each other, right? And that also lets me extract these alpha, beta, and gamma parameters, and that's what's shown here, right? They all sort of collapse onto each other. And so, in fact, this distribution as from PT has this interesting feature that already looks like a thermal distribution in 2 dimensions, right? It goes as basically as 1 over PT. So if you expand out your Bose distribution in 2 dimensions, that's what it would look like. Any questions at this point? Yeah, feel free to stop me. So in fact, this is what the picture looks like. So this is a plot. This is an actual result of numerical simulations that are shown here. That you find that, so here this is kind of a little complicated plot. You start with some very high occupancy and you're decreasing occupancy. Here's your classical fields and evolving in time like this. And you find that as a function of time, the anisotropy of the pressures, the momentum space anisotropy also increases. So you go away from thermal equilibrium. But you find that the system flows to the same point, the same kind of line in this occupancy and isotropy plane. Okay? And so this is really this remarkable thing, and it was extremely useful because it helped distinguish between various different conjectures that people had for what the dynamics is about the pre-equilibrium state of matter, which is this Glasma. Okay? There are all kinds of speculations that there are plasma instabilities, there are Bose-Einstein condensates, and so on. Okay? And I don't know if it actually completely settles all those questions, but it makes some progress in that direction. So for example, there were different scenarios. And so for example, there was one argument saying that you have just elastic multiple scattering of these gluons, which is dominating the initial non-equilibrium state of this matter. That there are also plasma instabilities influencing this, and you may hear about this in Kurkela's talk. I'm not sure. And then there's also possible Bose-Einstein condensation going on in the infrared. So the Glasma could form a Bose-Einstein condensate of some form. Okay, there's nothing that says from first principles that for very finite times the gluons in the Glasma cannot form a Bose-Einstein condensate. It doesn't violate any principle. And in fact, this is something to keep in mind, right? It's called Gelman's totalitarian principle, which says that anything that's not forbidden is allowed. Okay, so, and that's the essence of quantum mechanics. So there are lots of possibilities, right, which satisfy Gelman's criterion, which don't violate anything, so which makes this physics very, very interesting. In some ways, it's more interesting than a thermal system because the variety of possibilities are more complex and give you interesting forms of matter, right? So for example, in the Quark-Gluon Plasma, you don't talk about turbulence, or you don't talk about Bose-Einstein condensates, for example. It's this purely thermal system. So what's actually going on, right? So you can think about in this non-equilibrium regime, you have scatterings going on with some scale QS, okay? And And all the differences between these different approaches, right, that you can have in the Glasma come about because we really don't understand the nature of the screening of the interactions that are going on between these hard objects. Okay? And the reason is that the physics is starting to get non-perturbative at this scale, right? So when momenta become very soft in Yang-Mills theory, right, they start becoming non-perturbative. Okay? And the non-perturbative, remember, has nothing to do, right, with the coupling. The coupling can be very weak, but it can still become non-perturbative. Okay? So even at very, very weak coupling, at G going to 0, right, when you reach the scales of the Debye mass, the physics becomes non-perturbative. Okay, and so you have to worry about how you treat this non-perturbative behavior. And as you saw in Peter Petretsky's talks, right, there's lots, even in equilibrium, right, there's many different ways to organize the non-perturbative information in infrared. So even when you're computing the pressure in equilibrium in finite temperature field theory, in the infrared, you have to make certain assumptions about the non-perturbative behavior to really kind of match, say, for example, lattice data. And that's amplified when you're out of equilibrium. And so that's why we have all these different possibilities that could happen. So, it turns out that when you do this, this numerical simulations, one can extract results, okay, from this. And it actually turns out that these results are matched by a kinetic theory, okay, approximately, where you have just small angle scattering of gluons, okay? You have energy conservation and number conservation. So just like 2 to 2 scattering, basically, right? Where you have just small angle 2 to 2 scattering. So in other words, when you have these kinds of scatterings, they're dominated by very small momentum transfers on the order of the Debye mass. So these same, so it turns out the numerical simulations, this kinetic theory, right, gives you these values of these exponents, and these are the exponents within some important errors that are obtained in our numerical simulations. Okay? And these very same exponents appear in the bottom-up thermalization picture of Bayer, Mueller, Schiff, and Son. Okay? So what we would claim is that one of the major results of our non-thermal fixed point that we discovered was that in addition, it allowed us to kind of weight a little bit towards this kind of explanation of what's going on. Okay? But the reality may be more complicated, but at least it adds more information about understanding what is the right kinetic effective theory of what goes on in the Glasma.
Raju, so here the coupling constant is fixed, right? It's not flowing with.
No.
So it's weakly coupled. That's why it's matching to kinetic theory.
Right. So it's classical statistical simulations, right? So you're always working in the regime of G going to 0, right? And so of course you're not including loops and so on in that, right? Because whatever loops there were, you've included in the initial conditions. So you're not including further loops along the line. Right? So in the limit of G going to 0, one could argue that this is an exact representation of the theory, because all quantum fluctuations, in addition to that, are highly suppressed, right? Because they are at most of order 1 at any given time, right? So when you go to G going to 0, all those quantum fluctuations will never matter for this discussion. So this is QCD in that sense, that limit. So only there will be an overall running of the coupling which will match the hard scale of your theory at that scale. Okay, so.
Raju, excuse me, is the non-thermal fixed point that you mentioned corresponding to the thermalization of the soft components in the bottom-up scenario, to the formation of the soft thermal bath? Because then, so is this non-thermal fixed point corresponding to the formation of the soft thermal bath in the bottom-up scenario?
It's much before.
Is it before?
Yes, I'll come to that in a second. Okay. So. Because you asked the question, my answer to the question is part of the time here. but let me just address, I hope I have the slides. I'll actually talk about it in a second. So let me just go through very quickly to this bottom-up scenario, right? So in the bottom-up scenario, you have the scattering of 2 gluons, right? And remember, in the classical field, the momentum of the gluons is QS, right? It has transverse momentum QS. And so these two guys scatter and they have some momentum exchange which is given by Debye mass, right? And you can write this Debye mass as an integral over all the hard modes divided by this momentum, and that's where this infrared sensitivity comes in. Now the claim is that, remember that the pressure, right, is, even though it's decreasing, the pressure is not decreasing as fast as you would if you had free streaming, right? If the system were just not scattering, right? So suppose it was just, the gluons were just exploding into the vacuum, right? They were not rescattering, then they would follow this curve here. Okay? The fact that they don't follow the curve, and they actually move away from the curve, tells you that scattering is going on. Okay? So it's not being very efficient, but it's going on because it's not still exploding out, right? It's not free streaming. That's very important. And that's, you know, and the fact that, you know, it has a universal form tells you that there's some equilibrium that's maintained in some sense, right? Not thermal equilibrium, but a kind of equilibrium. So, so you can actually compute, you know, what the buildup of PZ is, right? Because if you just had free streaming, then you would just have PZ going as 1 over time, right? If the system is just free streaming, the redshift is as a function of the expansion of the system, so it's 1 over time, okay? So, but PZ is actually greater, and the way you understand it is because you have multiple scattering of these gluons that's going on, and so it's a number of collisions times the m Debye squared scale, right? So each of these gluons is getting a kick of m Debye squared, and if it gets many kicks, it gets some PZ, okay? So you can think of this as the PT direction, and PZ is this direction. So if I get lots of kicks, I develop some PZ. Okay? And so PZ, then, even though it's decreasing, it doesn't decrease as 1 over tau, it decreases 1 over tau to 1/3. Okay? And so it's a much slower parametrically decrease of PZ than you would get otherwise. Okay? And so now what happens is that this whole picture breaks down at later times. Okay? And where that breaks down is when the classical distribution becomes, when the classical occupancy becomes less than 1. So remember, I started out with some classical field occupancy, which is 1 over G, right? So my single particle distribution was of order 1 over alpha S, right? And so the occupancy was 1 over alpha S, but then as time increases, right, this occupancy is decreasing, and for tau greater than 1 over alpha S to the 3/2, right, this whole classical simulations that I was doing just breaks down. I can't use it anymore. But I have quasi-particles, right? So I can use kinetic theory to describe these quasi-particles. And that's the essence of this bottom-up thermalization picture, that initially you have classical fields, the system then goes to a non-thermal fixed point, already in the classical regime, and then you have scatterings a la Boltzmann type scatterings, right? And in there, 2 to 3 processes become very important in that. Okay, so what happens is that in the quantum regime, thermalization proceeds through number changing processes. So 2 to 3 becomes very important. And this is the answer to Edmo's question, that the fixed point happens well before 1 over alpha S to the 3/2, right? Because it happens before the occupancy becomes less than 1, but then the soft bath occurs for 1 over alpha S to the 5/2. Okay? And the system then thermalizes at a temperature of alpha S to the 2/5 times QS. Okay? Now, I want to impress upon you that this is truly, truly remarkable, right? Because I'm claiming that from first principles, okay, with a little bit of magic thrown along the way, okay, but that magic is kind of robust because you really see that in these numerical simulations, that the system flows to a non-thermal fixed point. You can actually compute all the way, right, the thermalization of the system in the Ray-J limit, and compute a temperature which just depends on the coupling constant and QS. So from the wave function, the properties of the wave function, I can extract the thermalization time and the temperature. Okay? And that's really quite amazing. And this was already prefigured in the work by Bayer, Mueller, Schiff, and so on. But then everyone thought they were wrong for a long time. But I think our work actually gave sort of reinvented the validity of that work. The other thing I want to tell you is that a lot of people tell me that, oh, you guys are working at alpha of 10 to the minus 5, okay? So your thermalization time is huge. So it's totally irrelevant for heavy ion collisions. And what I want to tell them is that completely wrong, okay? In fact, as the coupling goes to 0, the thermalization time actually gets faster, okay? So why is that, okay? So here's my statement. As the coupling goes to 0, right? Not exactly 0, but towards 0, the system thermalizes faster and faster, okay? And at some level, you should think that it's not too crazy because the occupancy is going as 1 over g, so, I mean, it might be the case. But you can see it from this formula, right? So, of course, if I put alpha being very small, tau becomes very large. However, it's absurd to choose a value of alpha, which is 10 to the minus 5, and choose a QS of 2 GeV. Okay, some people do that, and that's idiotic. Okay? There are papers written where people say, oh, I put 2 GeV here and I put alpha of 10 to the minus 5. No, you should choose a commensurate value of QS which matches that alpha, okay? And that would be beyond the Planck scale. So another way of putting it is that alpha is a log, right? Alpha, so what is alpha S, right? So alpha S goes as 1 over log of QS, okay? And so as you have very small alpha S, that corresponds to large QS, okay? But there's a factor of 1 over QS sitting here, okay? This factor will always beat a log, okay? So even though this is becoming a big number, this is becoming a very small number, okay? And so asymptotically, thermalization time will go to 0. So some of you may be familiar with this whole debate about, high multiplicity collisions at the LHC and so on, right? And saying you produce lots of particles as the system thermalizes. Okay? If the QS of that system is large enough, suppose I produce 300,000 particles in a PP collision. What this will tell you is that that PP collision will thermalize, okay? Because QS will be so large, right, that the thermalization time will be much smaller than the size of the proton. Okay? And so for some time, the system will behave hydrodynamically. Okay, so this formula and these results have very interesting, profound consequences which are non-trivial. But my point that I want to emphasize is it's absolutely inconsistent to choose a value of alpha which is very, very small and QS which is, also small. Right.
So once you produce this soft blot of gluons, then the typical Q exchange, and which will be involved in the scattering of these gluons themselves, will be where perturbation theory cannot be applied because Q square will be small. So there will be certain,
No, what I'm saying is that this QS is the initial.
No, I understand that, but I'm saying that the question is how far these estimates can be trusted, in the sense that.
So my statement is that in the Raju limit, right, these are very large temperatures. So everything that I'm saying, right, is robust in asymptotics, okay? Just like when you work in Toft coupling of infinity, things are very robust. You get very well-defined results, okay? The moment you start relaxing that, then all these questions come in, right? So if I take QS of 2 GeV, is that big enough, small enough, and so on? All I'm saying is that what we have shown that at least in some limit of QCD, okay, you can get well-defined answers to questions with at least parametric dependencies which are non-trivial. Okay? And these tell you that the system will thermalize in that limit. Okay? It will thermalize very quickly in that limit. Now, whether in practice in an actual heavy ion collision at the LHC, the system thermalizes depends on how far you can carry these extrapolations up or down, right? So there are simulations actually by Alexei Kurkula and company. So this is actually the full picture. So let me just, since I'm really running out of time, let me just say that this is the final picture that one gets. So there's a classical regime where you start far from equilibrium, there's a loss of memory, you go to a non-thermal fixed point, then the occupancies become small, but then you can use kinetic theory, and then the system flows to equilibrium with this thing here, right? So now, what Alexei Kurkula and his collaborators have shown, and then Zoran Schlichting, also with Alexei and others, have shown, is that actually, if you extrapolate this to realistic couplings, then this kinetic theory actually just matches to hydrodynamics. Okay? And the time scales that actually it matches to hydrodynamics, if you put some numbers in, then it turns out that these time scales are actually very reasonable for the phenomenology of heavy ion collisions. Okay? So because of that, you can actually even argue that this weak coupling picture, when extrapolated to realistic coupling, gives you a full soup to nuts picture of how you go from these Glasma initial conditions to hydrodynamics and thermalization. Okay? So, but it involves then really relying on the idea that no new physics comes in when you extrapolate from alpha going to 0 to realistic alphas. And that's a whole separate story.
Yeah. So, I mean, it looks very counterintuitive, right? I mean, when your coupling constant is very small, you expect your, particles to interact less, and the thermalization time should increase in that sense. But what you are saying, because of that QS thing, it's happening the other way around. So,
no, I would actually argue that was sort of the whole theme of my lectures, is that you can have strong interactions when you're recoupling when the number of particles is very large. Okay? So what matters is not just alpha, but it's alpha. It's not just alpha, but it's alpha times n. Okay? So for arbitrarily weak alpha, if you have n on the order of 1 over alpha, then this is a order 1. And so it's not counterintuitive if you think about most systems in nature, like cold, Bose gases, for example. Right. Their effective alpha is very small. Okay? Or if you look at condensed matter system, alpha electromagnetic is very small. Okay? But in most strongly correlated systems, it's this object that matters, not this. So from that point of view, it's completely in line with many body physics in essentially every other system that you can think of.
Thank you.
So, but actually, this radial limit you would also get in QED. So, but it happens at much, much higher energies because alpha electromagnetic is very small. But there, actually, the saturation there is like polyblocking in the sense that in QED, what you do is you produce electron-positron pairs, and at some point, the occupancy of electron-positron pairs becomes of order 1. That's the main difference. But other features of what I'm saying is actually truly universal. So in fact, I have a whole part of my talk which is showing that the stuff that we had is completely universal to that of cold atomic gases. Okay, and this is, you can read about this in this paper. I don't know if Zoran's going to talk about this in his talk, but we find that this non-thermal fixed point is exactly the same as what we get in a scalar theory. Okay, and so it's completely, so in fact, you can map the two distributions right on top of each other. So here's a gauge theory, here's a scalar theory. And for expanding scalar theory, so if you take cold atoms and you let them have the same kind of boundary conditions, then you find that the cold atoms and the gauge fields have identical scaling exponents and functions. Okay. So this physics of the Glasma is really universal and in a completely non-trivial way. So this is, again, saying that this physics is not just unique to the quarks and gluons, but it's also exhibited by other fields and by other kinds of degrees of freedom in other theories. So in fact, if you try to understand this from kinetic theory, it would just fail right away, right? Because in kinetic theory, in a scalar theory, you have all angle scattering, while in QCD, it's small angle scattering that dominates kinetic theory. So you would think you would get completely different exponents, but you see that in this case, you get almost exactly identical exponents. So there's something very non-trivial that goes on in actually, and that's the magic that gives you this fixed point, this non-thermal fixed point. But it's truly universal. Anyway, so are there any further questions, or? I think I've exhausted everybody. Myself.
Any questions?
So by the way, this plot, right, that I have here was the selling point for a $12 million research collaboration in Germany called IsoQuant. Okay, this was on the front page of the research proposal for that, and it actually got funded. Okay, and so this plot here that I'm showing you, these connections are so intriguing that cold atomic physicists are now trying to mimic the kind of things that you see in the Glasma. Okay, and so they're trying to, and they actually then there's a kind of reverse synergy going on between the two. So we have a big collaboration at Heidelberg, of which I'm a member. I'm an external member, and where there's sort of this crosstalk between QGP theorists and cold atomic physicists and people doing strong field QED who are trying to understand this physics more deeply, these universal features that I talked about. So I'm not lying to you. This is actually on the front page of this proposal that won this $12 million proposal that's supporting a lot of graduate students right now. Okay, so anyway.
Okay, so as it was last lecture by Raju, I think we can say to him a big thank you.